Okay, so we're talking about math. We did squares here. And again, I'm really relying heavily on you guys to go through the math project in lab and find out where you're weak, ask questions. I don't have time to cover everything in 309, but I do want to cover circles.
Yes, please. Yes.
Circles. All right, so with circles, you have to remember a couple of things. This right here is the center. That's where all the nougat is. This to this is called the radius. From here to here is called the diameter. And all the way around, circumference. Let's see, circumference, K-U, no. It looked right? C-I-R, this is why I have my paper, C-U-M-F-E-R-E-N-C-E, circumference. All right, and I don't like you to have to memorize a lot of formulas, so I'm pretty good about giving you formulas. But I don't always tell you things, you know? It's like, if I want to know how many cubic inches, not cubic, thank you, square inches are in here. And yeah, you can get square inches in a round thing. I may ask you, how many square inches? How many square inches? That's not right. Come on, get with the program here. No more scotch during breaks. How many inches squared? There we go. How many inches squared? Well, and then I would say, first you got to have, using the formula, so the formula is area equals pi r squared. And I would say, using the formula, pi r squared, tell me exactly how many cubic inches are in this circle. And then I would give you a circle like this, and I would go like this, and I would say that is 6 inches. And that's how I like to write a test. Did I help you out much?
Then that would be 3.14.
Okay, so I said the area is pi times the radius squared. Actually, I take that back. I wouldn't have done that. Let me go back to what I would have done. I wasn't thinking here. I would have said this. That right there. That right there is 6 inches. Okay. What did I just tell you is 6 inches?
Diameter.
What do you need to know?
Radius.
All right, so how do I get the diameter, or the radius out of the diameter?
Half.
It's half. So, well, you can see that. So it's, so I need half. So the formula then is area equals pi times, what is my radius?
3.
So the radius of this is from here to here, which is actually 3 inches. So it's 3 squared. This is where we get into order of operation. Things don't necessarily go from left to right. I like to remember, please excuse my dear Aunt Sally. Although there's a better way to write this, because I don't like to write it. It's actually, please excuse my dear Aunt Sally. And this is a much better way to write it. And the reason why is because the P is parentheses. So we should always do anything in parentheses first. So if we have parentheses or brackets, okay, that is the thing we do first. Then we have to do exponents. E-X-P-O-N-E, exponents. And that is the square. So exponents are the squares. Then we want to do multiplication, and division from left to right. They are equal in each other. So it's not, when I first saw this, I'm like, wait a minute, so first do division and multiplication, then do division? No, it's multiplication, division are equal, done left to right. And then addition and subtraction are the same, equal from left to right. So if you can remember, please excuse my dear Aunt Sally, we're going to look at this, we're going to say area equals pi times 3 squared. So what is the first thing I must do? Do I want to go pi times 3?
No.
No, I got to do my exponent right here. So first I have to know what 3 squared is. So 3, and that means 3 times 3. But on your calculator, it's not hard to do. If you can't remember 3 times 3, we're going to do 3. And it's this little one here with the little rooftop on it. Am I right on that? There's also a square here too, limit square. So on, clear 3, second equals, yeah. So this little guy, this little roof right here, that will allow you to do exponents. So I'm going to do 3, the roof, 2. And it should be an x squared. Right here is x squared. I think it's the same thing. Clear 3, x squared equals. Yeah, so there's a shortcut right here to squares. But if I had later on, if you have to do something like 3 cubed or 3 to the 4th, you'd use a little house. Or you can use the little shortcut here for squared. So they both will do the same thing for you, depending on for squared. So 3x squared. So 3x squared equals 9. That's 9. So area equals pi times 9. And there should be a little pi button on there. Where's my pi button on this new calculator here?
28.27.
Tell me where the pi button is. It is Alt tab. Go back to here. My pi button. Pi is right there. Look at that. I can see it when it's big. So here's my pi button. So it's 3. So 3x squared times pi equals. So that's exactly do it. 3. Then I hit the x squared. Then I hit the pi. Then I hit equals. And my answer is 28.27 is the answer I get, and that is inches squared. Square inches, that was what I wanted to know. All right, what else do we have to cover? Let me just take a look at something here. You just talks to amongst yourself real quick.
Well, I mean, that's a deep conversation.
I don't want to take up too much time. That's enough. Does anybody have anything they want me to cover on their little math sheet that you didn't understand how to do?
Yeah.
No, now we did it.
Make it count. You only get so many.
Yeah. What's your problem? No. Shh.
You got it?
What? I was looking for something else. I think we're good. I think we covered everything that I really want to cover right now. Yeah.
What about number 27?
I don't know number 27 off the top of my head.
5,924.
Hey, I can't hear Charisse.
We're converting into a
Aaron, you're still talking.
Sorry. Converting to a scientific notation is 5,924.
5,924.
And it's 7/8.
Well, it's,
Or 7 divided by 8.
okay, I tell you what, this is too difficult to take up to it. We'll talk about that in lecture or lab, okay? Is that okay? All right, so I want to move on from here and shift gears, and let's get into some electricity with what little time we have left. All right, so to understand electricity, we need to know what electricity really is, what's really happening down there, and that really comes down to the molecular level. So in order to discuss that, we have to discuss the atom. Discuss atoms. Well, the atom is considered to be the basic building block of all nature, and I think that might even be an FAA answer to a text question. The atom is considered to be the most basic building block of all matter. Building block of all matter. It is composed of several things. So we wanted to draw a little atom. Let me think. I want to get my colors going right here. I get an atom. So in the atom, we have this nucleus. So we'll draw an atom over here, and we'll kind of do that and say that is my nucleus. Nucleus, my nucleus. And inside of the nucleus, we have things called protons and neutrons. So I'm going to give two little things here. I'm going to say, well, those are my protons. Protons. And here's another proton. Proton. So I have two protons. So not only have protons, we also have something called neutrons. And I'm going to give myself two neutrons here. I'll make them green. So that's going to be my neutron. So inside of the nucleus, which is the nougat center, is really not nougat, I don't think. It's too bad. There are protons and neutrons. And protons have a charge. And their charge is positive. Now, the interesting thing about that is, why is it positive? Well, at some point, somebody just said, you know what, I'm going to call that little charge positive, and everything worked out from there. And so they said the neutron has what kind of charge?
No charge.
Well, you want to say negative because it starts with M, but it has no charge. So I'm just going to put a little, I'll just do this, I'll put no charge, just kind of like that, no charge, has no charge. And then circling out around this, and if we do a very two-dimensional model of an atom, which is very two-dimensional, they say orbiting around this in a shell, so this right here is my shell, is electrons. And electrons have a negative charge. So I wrote my protons with my positive in red, and my neutrons is a neutral in green, and electrons is negative in black. So we can let that be a reminder that positive is red and negative is black, and that is the industry standard. And we can write this over here. So you got it inside the nucleus, nucleus is, we have the center of the atom. It's the center of the atom. Contains protons and neutrons. Protons and neutrons. Hey, maybe I should go get my Bill Nye the Science Guy lab coat on for this, this particular.
That show.
If you have it in your office, that would be great.
Man, oh, man, that's like nostalgic right there. Bill. Bill Nye the Science Guy.
All right, we're going to talk about protons and neutrons with the Bill Nye the Science Guy.
Now you look like Kit.
Well, that's not a bad thing.
No.
So you may hear the name Kit mentioned. Kit actually Kit was the teacher before me, and he's still alive. But Kit is loved by everybody who has ever met him. Huge shoes to fill, but he was only this tall. So they weren't that big. But he was my teacher way back when. So was Phil, actually. And so Kit always had his. Mine has got grease from Katie and NDT fluid in it. So, all right.
It looks good on you, sir.
Yeah, thank you. I have a blue one too, if you'd like. We say it contains protons and neutrons. I lost my place. Protons are what charge? Positive. Positive charge. And that leads me to the neutrons are neutral. Charged. Well, and then we have our electrons, which is really what electricity is all about. E-L-E-C-T-R-O-N. Electrons. And this is actually quite hot. Electrons orbit the nucleus in shells. The nucleus in shells. Well, luckily for us, the FAA likes the two-dimensional model of the atom. And so we can make this very simple and have this two-dimension, and it works. And so we're fine. But I want you to know something, that the atom doesn't really look like this. It looks kind of like the one, sort of, in the show with the guy in the...
Jimmy Neutron?
Jimmy Neutron. That's even better than I was going. Jimmy Neutron, and the guy was Sheldon. What's his name? The
Big Bang Theory.
Big Bang Theory, right? Yeah, you see.
Yeah.
Okay, so that's more of the simplistic 3D model. But even that is not accurate, and so the real accuracy one is they actually talk about how these electrons, they're not circling around like planets circling a sun. They actually have probability of where they are, and they buzz about. And where they are, and it becomes this probability, like they're probably going to do this, and so it gets really complicated, but we can pull it all the way back and go to a two-dimensional model, and the FAA is happy with that, and it works, so just know that's where we're going to stick, because if they're happy, I'm happy. And actually, how's it go?
Really breaks down.
If I'm not happy till you're not happy, all right? So, all right, so now these shells are like, they're... If you can, again, if I go back to my analogy, like planets orbiting, well, these two planets right here, they're like little moons, and they're all on the same path. But that's one shell. And then there's going to be another shell out here that's going to have more of them and more, because you can only have so many electrons in each shell. All right? And so there's a formula to figure out exactly how many you can have in each shell. And I want to tell you that. So the number of electrons... let's see. Do I want to get that? Oh yeah, we can. I'll just back up just a little bit here, and I will tell you if the number of electrons, because I should have mentioned this, number of electrons equals the number of protons. In other words, my little atom that I drew, I have 2 protons, 2 neutrons, and 2 electrons. That is a neutral atom. And it's supposed to be that way. You're supposed to actually have that many. It matches all the way across, sort of. Okay. The atom is neutral. Electron, the number of protons, the atom is neutral. An extra electron. Okay, if I have an extra electron, something happened and this atom picked up a 3rd electron. What kind of charge is it going to have now? It has more what's to it? It has more negatives. So an extra electron is a negatively charged ion. Negatively charged ion. And if it had an extra proton, and has an extra proton, what do you suppose it's going to be? An extra proton is a what? Positively charged ion. What is an ion? Well, it's a defunct Saturn car. That's all you need to know. All right. Electrons. They're fast little suckers. Electrons move about. They move about at about. Electrons move at about the speed of light. The speed of light, which is equal to 186,000, miles per second. Miles per second, which is a lot. So let's verify this. Yep. It works better if you have a longer distance. That's how I figured it out. I just watched my watch and how long it took for the light to click on and hit that door, and I used my watch and I did the math, and that's what I came up with. So All right. Depending, come back here, depending on how many electrons there are and how they are arranged, well, first of all, makes up what kind of atom this is. If I remove this atom, a 2, 2, and 2, who's my physics genius in here? What kind of atom did I make up?
Wait, say it again?
2, 2, 2, and 2.
Oxygen.
Hydrogen?
I think it's hydrogen. No, oxygen is
No,
Oh,
yeah,
oh,
it's hydrogen.
it's hydrogen. Normally you do 1 and 1 and 1, which is helium. Yeah. So 1, 1, and 1, that's helium. 2, 2, and 2, hydrogen, I think. And so depending on how many atoms and how this is made, exactly how many protons, how many electrons determines what this atom is. Now, depending on its makeup, not only does it dictate what it is, but it also dictates if it is an insulator or a conductor. So as the name implies, a conductor is somebody that drives a train. Thank you. That's what I was looking for. Drives a train. It also conductor conducts electricity. All right. And an insulator is something that keeps you from dying.
Yeah, I like insulators.
The insulators are my friend. All right. So where am I? Depending on how many electrons there are. How many electrons there are, and how they are arranged, around the atom, well, actually is the atom, will determine if the atom is an insulator or conductor. So a conductor will allow movement of electrons. And an insulator will prohibit the flow of electrons. An insulator will prohibit the flow of electrons. Within reason. If you put enough voltage across anything, electrons will flow. That's called breakdown. So let me think here. If I had a nice little thin piece of rubber, like a piece of paper, is that an insulator or a conductor? It's an insulator. I take that nice thin piece of rubber and I wrap it around my hand and I grab 100,000 volts.
It's not going to help.
It's no longer an insulator, is it? That's what we call it. So enough voltage and anything becomes, it's not really a conductor, but electrons will pass through. Okay, let me see. Am I getting this? I do. All right, we're heading somewhere. All right, so if we know this, so far now we've learned a couple things. One, we know that how the electrons are arranged will dictate if and how many there are, if it is an insulator or a conductor. So what is really electrical flow? So electrical flow. So electricity then is the movement of electrons from one atom to the next. Movement of electrons from one atom to the next. The fundamental, F-U-N-D-A, The fundamental principle is attraction and repulsion. So, all right, attraction, repulsion. Well, how is this going to come into play? Well, it is said that opposites attract. And why do they say that, and who is they anyway? So, unlike charges attract. Unlike charges attract each other. So, if I have something that has a negative charge, and I have something that has a positive charge, hang them on a little string right here, are they going to want to come together or go apart? They want to come together. Okay, so these two things are going to come together, and they're buddies. But if I hang something over here and say, well, you get to be a positive, and you over here, and you're a positive, they want to? They repel. They hate each other. They don't like each other. I don't know why. I don't know what beef they got with each other, but they don't. So they want to repel. These two things want to come together, so it's going to be
kind of like you want to be king and I want to be king, but we both can't be king, so one of us, you kind of push away from each other. You're not in the same goal.
And that makes sense. And so we've got, that's the two positives. We have two negatives. I don't want to do anything, you don't want to do anything, so let's hang out and do nothing together, right?
Yeah.
Okay. No, that wouldn't work.
Both of us aren't
That's
doing anything.
separate. Okay, you don't want to do anything, and I want to do all the work, so we're going to...
I didn't see it. You go that way, I go this way.
That did nothing about that worked. All right. All right. In addition, protons, and electrons create stability. So what we have going on around our, I'm going to scroll, well, I'm not going to, I'll just do it over here. So inside of our atom, where we've got protons and neutrons, and we've got rotating around here, we've got the atom rotating around. We have the positive on the inside and the negative on the outside, and so are they attracted or repelled?
Attracted.
Okay, so the rotating atom is actually, the electron is actually attracted to the nucleus, but it doesn't just pop in there and stick in there, right? We just use kind of silly terms, because there's energy with these electrons going around. So they're too busy to stand still. I suppose if they were come to stop and lose their energy, they would get sucked right in the middle. But they're buzzing around doing their little electronic thing, and so they have too much energy to just be yanked back in, but they are attracted. But if we look at it and we say, well, we've got this electron, we have this electron here and this electron here. These two are not, they're repulsed by each other. All right, and then if I put another one over here, rotating around, they're going to be repulsed by each other, and so forth. And so it's going to go. So all of the electrons are kind of repulsing each other. Repulsing.
Same thing.
Yes. Okay, so I want to bring that. So, and of course, I'll just fill this in because we already talked about it. Like charges repel. Like charges repel. So we have this repulsive force going on. I'll draw this. So So through the magic of whatever this is called,
Art.
my artboard here, I have these electrons right here, and they're all kind of lined up. And we'll just say this is a very simple piece of copper. So I've enlarged it. Here's my wire. I just enlarged it really quick, and we'll come back down to normal size. So inside there's copper. And copper is a great insulator. And so I decide I'm going to hook this up to a battery. I'm sorry, conductor, thanks. So I hook this up to a battery, and I'm just using black. And this is my positive, and this is my negative. So I attach my battery there, and my battery there. Whoops, I better put a light on it so we know it's working. So the light's on. Okay. I'm going to have electrical flow, and I have to remember a couple things. Like charges attract or repel. Like charges repel. Okay, so like charges repel. So this is a negative, and so that means that it is going to attract or repel other electrons. repel. So it is going to force electrons to go this way. Right in this, it's going to force this one to go this way and this way and this way. It's going to force them to repel. And unlike charges do what?
Attract.
So this negative right here is attracted to
Positive.
the positive. Therefore, the flow of electricity is from.
Negative. Positive.
Therefore, the flow of electricity is from negative to positive. That looks like taught. From negative to positive. There we go. Now the funny thing is, I don't know, I think it was around in the mid-50s, they sort of figured this out. So up until then, everything was, do you remember when they did that?
Yeah. Yeah, I was there.
It wasn't, I think it was about the mid-50s, like around 56, when they actually kind of figured that out. And because of that, it was then always said, well, electricity flows from positive to negative. And the point here is that in basic electronic, or basic electricity with especially analog stuff, it really doesn't matter. Because they thought it went one way for the longest time. Realized, well, I guess it actually goes the other way. It still works. But the interesting thing is, the way the convention is, because of that, our drawings never change. And so if you're troubleshooting something, it is so much easier to troubleshoot it as if electricity went positive and negative. Everything, right, Rich? I think.
It's the way you still do it.
Yeah, you troubleshoot it like it flows the other way. So a lot of times if we're talking, I'm doing troubleshooting or we're working something, I'll actually show the flow going backwards, especially on a diagram or a chart. You go, wait a minute, this guy forget his own rule? No, it's just the reality of it is it flows from negative to positive. Out in the field, we treat it like it flows the other way because it makes more sense to troubleshoot stuff that way. So,
Well, is that mostly because that's the way like you guys like learned it?
no, it's actually drawn that way. It's drawn that way. So I don't have too much time. So this is a battery. I'll just make a very simple circuit with a light bulb and a solenoid of some sort. We got a solenoid going here. This comes down. Here's a solenoid which goes to a switch, and the switch comes down. And so,
Yeah, it's true.
all right. Now it's very simple. So the point here is that to try and these are all ground symbols, because that's really how an aircraft is grounded. You go to the component. Off the battery, there's only a little short jumper that goes to ground. Off any light bulb, there's a little tiny wire that goes to ground. So electricity is really, truly flowing this way and up this way. But it's so much easier for me to go, okay, here's my battery. The wire comes around and goes to my light bulb and then goes to ground. Then it comes over here and it's going to stop there, but it comes around here and it's going to go into a solenoid that's looking for a ground. So when this switch is closed, it's going to close this solenoid and it's going to act something. It's too hard to, because these drawings are laid all out. And you're like, okay, so it comes out of this ground. And then you're looking through an entire drawing, looking for another ground. Where's it going? Where's it going? And to go up, it just works to follow the line. So you follow the line. All right. I think that's all. Yeah. Okay, before you take off,